I'm at the University of Tennessee. I also hold a position at Oak Ridge National Lab. And one reason why I'm talking today and not next week is that I'm going to Manchester on Saturday. So I have a position in the maths department at University of Manchester in the UK. And I spend about a month there, and this year it's in August. Okay, so what I'd like to do is to talk about dense linear algebra. So we're going to be talking about solving these kind of problems where the matrix is dense, so not sparse. We're going to be using direct methods, not iterative. We're going to be looking at how we could perhaps get performance on today's machines using these kind of approaches and methods. So solving systems of linear equations, looking at least squares problems, solving eigenvalue problems, singular value problems. And these come up in many applications. So here's a list of the applications they come up with. They come up in, and just to keep in mind, we have a matrix, usually it's square, not always, but usually, and it's, we'll call it order n. So we have n squared elements in the matrix, dense. And in order to do a computation, we think about algorithms which typically take order n cubed operations, order n cubed. So matrix multiplies an order n cubed algorithm. You're going to be hearing about sparse techniques in next week, and those are different, quite different than these methods. These methods will usually work if we can compute a solution. You're going to get a solution as well as you can. And they, of course, have limitations because we can't solve extremely large problems, dense large problems on machines today. But we can solve some problems and solve them quite well on the architectures that we have. I've collected over the past few years a list of what I'll call freely available software for looking at matrix problems. And this page that comes from that page here, it should be a pointer, from this page here, has all the software I know about for doing dense problems. There's also on that page software for solving sparse problems, sparse direct problems, and a number of other things related. So if you're interested in looking at software, looking for software for solving these kinds of problems, you should go to this page. Freely available software. The licensing is explained, what kind of coverage there is in terms of sequential, parallel, distributed memory, GPUs, and so on. You can find out from the page. So one-stop shopping if you're going to do any looking. And there's no evaluation made, so I can't tell you that Petsy is better than Trilinos. That's not going to happen here. You have to make that decision yourself, but the information is there for you to at least kick the tires. So that could be a valuable resource. So we're interested in dense problems. The sort of state of the art, I'll say, in the 90s for doing this stuff was LAPAC and ScalaPAC. So LAPAC is a package of software for dealing with dense matrix problems, and it mainly deals with shared memory machines. And I'll show you more specifically what I mean by that. ScalaPAC was updated to do message passing, so it does distributed memory systems. Those were the gold standards. Those packages are pretty old today. Those packages are almost 30 years old. And in my life, I usually have to refresh software every 10 years. Architectures change. It requires us to rewrite and rediscover or invent new approaches for solving it on the architectures that we have. So that's a lesson that is painful, because rewriting software is not cheap. It's a very expensive thing. Software is very expensive, more expensive than the hardware. And you'll hear about some of the hardware that DOE is investing in, and it's extreme, right? So DOE has a plan to invest $1.8 billion in the exascale machines. They're going to buy 3 machines, $1.83 billion. That's for the hardware. The software cost is going to be more than that. Okay, so just keep that in mind. Software is very expensive, and especially when you have to retool applications. And we're talking about, applications which are intended to run at scale on these machines and intended to run at high performance. Okay, so that's what we're interested in doing. This is a summary of my life's work in some sense. So this is what I've done over the past too long. So I've looked at, I've been involved in these packages. So these are packages for solving dense matrix problems. So in the 70s, there was something called IcePack, which was a translation of some Algol codes that were written to implement them in Fortran to be portable. And those were eigenvalue codes mainly. LAPACK was a package. Many people think of LAPACK as a benchmark. It is. But it really is a package of software for solving dense matrix problems. And LAPACK was in the 80s. Vector machines were in the 80s. And LAPACK relied on vector operations, the things that today we call level 1 BLAs, working on vectors of the matrix. And today we know that's probably not a good idea, just a vector at a time. That was the scope. So LAPACK came in the 90s, and it was, architectures changed. They became, they had cache, and if you exploited cache, you could get high performance. LAPACK exploited cache. It dealt with block-based algorithms. So it tried to organize things around operations on blocks or operations on small matrices. Think of matrix multiply, while keeping the same number of operations. So it relied on the level 3 BLAS operations. And at the turn of the century, LAPACK was created to deal with message passing. So we had to retool this in a way to exploit MPI. And the way to exploit distributing the memory, distributing the matrix across the memory. Plasma is an effort, I'll call it a research effort, to take these ideas and to try to exploit parallelism at a much finer level in some sense, and to, instead of having what I'll call loop level parallelism, try to exploit a different form of parallelism. And the form of parallelism is through a directed acyclic graph. So the algorithm gets described in terms of a DAG, and then the DAG gets executed on the machine. And there's a lot of advantage you can extract from that in terms of freeing up the loop-based bulk synchronous processing. Today, we're working on something called SLATE. So SLATE is the package for dense matrix problems that's for ECP. So DOE's exascale computing program has many components to it, and you're going to hear about some of those. Our component at Tennessee is SLATE. So SLATE is the package that's intended to replace, I'll say, all the packages that came before it. It's going to be the, quote, state of the art. It's going to be the thing that runs on those exascale machines. It's going to be the thing that it tries to extract full performance. Okay, so let's talk about performance, since that's going to be the underlying theme of this talk and many of the other talks. I'm going to talk about 64-bit performance for most of this talk. I'll talk about 16-bit arithmetic later, but 64-bit floating point is what we think of for doing scientific computing. And we think about machines that have teraflops and petaflops, 10 to the 12 or 10 to the 15. Exascale, of course, is 10 to the 18. Operations per second. And whenever we say exascale, in that context, we mean 64-bit floating point operations. And by an operation, I mean an add and a multiply. We're not talking about divisions or square roots or sines or cosines. So we want to take a look at what the theoretical performance is, just because that's a ceiling. So if we take an example, and the example is, let's take an Intel Skylake. So an Intel Skylake has a processor which is at 2.1 gigahertz. So that's the cycle time. That's the issue rate for instructions. And every cycle, it can complete 32 floating point operations. Each core can finish 32 64-bit floating point operations per cycle. So that's a stunning number in my mind. 32 per cycle. So the theoretical performance is 67 gigaflops. Okay, so 32 times 2.1, 32 times 2.1 gives us that number of 67 gigaflops. And if we have a 24-core chip, you multiply that by 24. So that gives us 1.6 teraflops out of that one chip. That's the theoretical peak performance. So if I'm writing an algorithm for this machine, I'm going to try to hit that. I'm trying to get as close as I can to that. And if I can't get to that, why? What's limiting my performance? So that's sort of a fundamental question that's going to be going on here. This is a roadmap, if you will, looking back over Intel processors. So if we take a look at Intel processors, there was this fuse multiply add instruction. There's this early Xeon processors, had this SSE2 thing. So you got 2 flops per cycle in double precision. Single precision doubles everything. So we get 4 flops in that case. In 2009, Halem and Westmere came out with enhanced SSE4. That gives us 4 flops per cycle. Sandy Bridge and Ivy Bridge came out, again enhancing things, 8 flops per cycle, per core. Haswell comes out, and Broadwell, 16 flops per cycle, per core, with their AVX2. And today we're here with Skylake, and Skylake does 32 flops per cycle. So that's sort of where we are today, and there's Cascade Lake, and I'm not sure what that's going to involve. Maybe Tim will give us all the secrets. He says no, he's not going to do that. And just in case you haven't heard, this has been canceled. So there was a processor from Intel called Xeon Phi, Knight's Landing. That's gone. They've abandoned that architecture for the future. And so Skylake is the main runner, if you will. And the machine that is one of the exascale machines will have an Intel processor, and that processor is unknown at this point, right? So maybe Tim will tell us about that. Hell no for that. Okay. Tim's not going to give away any secrets today. That's right. So that could get you in serious trouble. Good. Yes. I don't even know about that. So that's where we are. If you take a look at, so we have this theoretical peak, which is incredible. What's holding back? So what's the big issue? It's about memory latency. So if I take something from memory on these systems, I have to wait. So we're not talking about in cache. We're not talking about in registers. I'm talking about in memory, so main memory of the machine. I have to wait, in some cases, 167 cycles. I do a load, and it's not in my cache. I wait 167 cycles before I get that piece of data, and then I do the operation on it, and then it goes like a bat out of hell. And it'll continue going that fast if I can get reuse of data. That is, if it sticks around, if it stays in cache and it stays in the registers. But if it doesn't, if I have to repeatedly go back out to memory, I pay that penalty. 167 cycles, oops, I was afraid I was going to do that. 167 cycles, I could have done 2,500 floating point operations in the time I'm waiting for that thing to come to me. That's an incredible amount of waste in some sense. So you heard Jim Demmel's talk yesterday about communication avoiding. It's all about this. You want to avoid this communication whenever possible. Minimize the communication that we do. And the communication in this context is about going from memory. I want to minimize that. So I want to keep things around here as much as possible. 4 cycles maybe to get something. All right? So that's a fundamental strategy. So let's take a look at what happens. I'm going to take a look at my laptop. So I've got a Mac. It has a dual core. Each of those cores, so the cycle time is 2.3 gigahertz. It has something called turbo boost. So turbo boost is something which will have the cycle time go up if it can, but it's not going to damage anything from a thermal standpoint. And it can raise the frequency by a factor of 50%. So instead of going at 2.3 gigahertz, it can run at 3.5, and it does. It does run at 3.5. So I've got a Haswell processor, 3.5 times 16 flops per cycle, says that each core has the potential to do 56 gigaflops on my laptop. This is a machine I use to read email. That's incredible. That's a stunning achievement, right? That we can see that in a laptop that has a battery that lasts probably 6 hours. Okay, so here's the architecture. I've got a CPU, I've got cache, 6 megabytes of cache on this machine. I've got a bus that delivers data from memory, 16 gigabytes of memory. That bus goes at 25.6 gigabytes per second. Those are all given to me by Intel and by Apple, I guess. So that's the model that we're going to use. I'm going to omit latency because it just gets in the way. And I want to highlight things. So that means I'm going to make my vectors very long in these experiments. So we're going to take a look at two simple operations. These are vector operations, a dot product and a DAXB, or AXB. AXB is taking a scalar multiple of one vector and adding it to another. And a dot product, of course, is doing an inner product of two vectors. Each of those things have two vectors involved. So in the case of the AXB, I multiply n things, I add n things, I do 2n floating point operations, and I issue n FMAs, fuse multiply add instructions. In the case of a dot product, the same situation is true. I do 2n operations, and again, I do that kind of thing going on with my operation. So very simple. I'm going to take long vectors. I want to get rid of latency, so I'm going to take long vectors to fill up cache. So in this experiment, I'm going to do a dot product, and my dot product says the data, I'm going to take two vectors of size 375,000, so very long vectors, multiplying them together. So the data is of size 375,000 times 8 bytes. We have double precision. So that says 3 megabytes per vector. That's the vector length. So the two vectors will fit into cache. So that was satisfying my goal. So the time to move those two vectors, I have to move those two vectors and then do some operations. The time to move it is 6 megabytes divided by the rate. So this is the peak rate, 25.6. So it takes 0.23 milliseconds to move the data. That's just moving data. The time to perform the dot product, I have 2n floating point operations. 56 gigaflops is the peak that I can see. So the time is 0.013 milliseconds. So this is nothing. The time to do the floating point is nothing. Right? So I'm paying for moving the data. That's where all the cost is going. So let's say I can overlap the floating point and the data movement. So that says the total time is going to be 0.23 milliseconds. And that says that the performance is 3.2 gigaflops. So the vector performance on this machine, theoretically, is 3.2 gigaflops. The peak performance is 56. So I've just lost more than an order of magnitude in performance by doing a vector of operation. Right? So that's communication bound. There's no reuse of data. I read data in, I compute, and I produce one number. And that's it. So no reuse. I don't get any benefit from that moving data. So those were vector operations. There's other operations we can exploit. Matrix vector operations. Matrix times a vector added to another vector, 2n squared flops, we have n squared floating point or memory references in the matrix. So the ratio here is 2 to 1. Notice the ratio here was 1 to 1. I want this ratio to be as high as possible. Flops per reference. If I do a matrix-matrix operation, I have square matrices. I have 2 n cubed flops. And I have 2 n squared memory references. So that says that the ratio is n to 2. This is great. This would be a great thing. This says there's a potential here to get a lot of reuse of data. There's no reuse of data here. There's very little reuse of data here. The only reuse comes in the vector x. X is used over the whole matrix. So what does my matrix vector operation do on my laptop? Again, I make things big enough to fit in cache. So the size of the matrix is geared to be 860. At 860, with those vectors, I get 6 megabytes. So the data fits in cache. And the time to move the data is the same. I'm moving 6 megabytes of data. The time to move it is 0.23 milliseconds. And then I do the operation. So the operation is 2n squared flops. At this rate, it says it'll take 0.026. So it takes a little bit longer than before with the vector operations, but we're an order of magnitude difference again. So data movement is killing us. No reuse of data, very little reuse, I'll say, of data. So again, let's take a look at the total time. It's dominated by the move time. The flops are immaterial, right? Doesn't matter what the cost of the flops is, much less. And we end up with 6.4 gigaflops is the theoretical peak. 6.4 over 56. A little bit better, but still we're wasting a tremendous amount floating point operations. And again, these operations are communication bound. Okay, so what happens if we raise the level again? Matrix multiply. We're going to multiply matrices together, and in the experiment, if we do things to, again, fill up cache, we have a matrix with size 500. 500, 3 matrices fill up cache perfectly. The time to move the data is exactly the same. The time to do the operations now, we have 2 n-cubed flops to do. So the time goes up. So it takes 4.5 milliseconds to do it, compared to 0.23. So now we're spending a lot of our time doing flops. And that's where we want to be, not in data movement, in doing flops. So if I can structure things around these operations rather than vector operations, I'm in better shape. So again, if we just go through the analysis, it says that for matrix multiply at 4.5 milliseconds, I can theoretically run at 55 gigaflops. 55 gigaflops is very close to the theoretical peak performance for this processor. And again, much better than what we have at vector or matrix vector. So now we have a chance of getting close to that theoretical peak performance of the machine. So how does it actually work? So this is the experiment on my laptop, running those BLAS operations using MKL, the Intel matrix kernel libraries, is the best that you can possibly do. So this is the performance for vector operations, for small vectors to large vectors, matrix vector operations from small to large, and for matrix multiply. So clearly matrix multiply has a chance of getting at that peak rates of execution. So that was on my laptop. This is my laptop. And this is on a Sandy Bridge. So this is on an 18 cores, using all 18 cores of the, Skylake. So again, you see vector operations way down here, matrix vector, and then matrix multiply exploiting little over a teraflop of performance. The theoretical peak is 1.3. So still we're leaving something on the floor, but overall we're getting a pretty good return if we could get matrix multiply for big enough matrices. Notice at the low end, there's a steep curve there that goes, but it goes pretty high, pretty quickly. By size 2000, we're up to close to the theoretical peak. So I want to structure my algorithms around that approach whenever possible, and avoid that memory-bound situation, exploiting that factor of 42 in this case for the performance of our things. Okay, so getting reuse is a big deal. Keeping matrices in cache is where we're going to get performance. Structuring things around that is going to be critical for high performance. And we may have to break things up. So if we have a large matrix, we may have to break it up into smaller pieces which fit into cache and structure the algorithm around that. I think of matrix multiply as having 3 loops, IJK, and if we're going to break things up like this, I have 6 loops, where the 3 outer loops are around these blocks, if you will. So that's one way of structuring things to at least have a chance of looking at performance in a reasonable way. Check it, please.
Yeah, so maybe I missed the point. So what if I only need the operation of AX plus B instead of a matrix multiplication?
You're hosed. You have no, if you're only going to do one operation, then you have no chance. So if you have a matrix vector product, let's say if you have an iterative method where the matrix is sparse, in fact, and you're going to multiply it by a vector, then the performance is going to be limited to that curve that I just showed.
Is there a way of converting my original problem to a matrix-matrix problem?
So it depends on the algorithm you choose. If you have a dense algorithm, yes. Dense algorithms, though, have this property they take order n cubed operations. Sparse algorithms, in general, take order n squared operations. So there's going to be a trade-off or a balance between those two. And where we reach that balance is how large is your matrix? How many iterations does it take to converge? Do you actually get the answer? Iterative methods may work. There's no guarantee they're going to work. You need a good preconditioner for them to work. So that's another thing which sort of throws something into that overall plan of using things. So there are certain limitations for dense matrix algorithms. One one of the limitations is the size of the problem and the number of operations that you do, which will lead to a higher time to solution. Sparse problems deal with sparse matrices. You pay a penalty in terms of the operation, each operation cost, but it may take fewer operations to converge, and your overall time to solution may be less. So those are things that have to be balanced in some way. So there's very likely to be no free lunch in this with sparse matrices. Okay, so back in the 70s, this algorithm was the algorithm that we decided to implement. So this was LU factorization. It's a standard thing that you learn, sort of the standard thing you learn when you do Gauss elimination with partial pivoting. Right, this is the algorithm. We're going to take a multiple of one row and add it to another row, introducing a 0 into it. So think of it, we're somewhere in the middle of this factorization. I've introduced zeros in this trapezoid. I'm working on this guy here. I want to introduce zeros down here. And I do that by taking a multiple of this row and adding it to all the other rows. So a multiple adding it to this one, a multiple adding it to this one, so as to create a 0 in that place. So basically I'm introducing zeros in this red column, and then I need to transform the rest of the matrix. I did an operation, I need to apply it to the rest of the matrix. And that updates all of these red elements here. So it changes all those red elements. And then we go on to the next step. So the thing is to introduce zeros into a column and then apply it to the rest of the matrix and then go on to the next step. That's the basic iteration. That was done through a level 1 BLAS operation. The level 1 BLAS operation took a rank 1 update. So this is a rank 1 update. I'm adding this column. I'm taking the outer product of this row and this column and adding it to the rest of the matrix here. And that introduces the zeros and applies the transformation. So rank 1 update. Rank 1 update changes a lot of information. So now I've got a lot of data movement, right? And it's structured like this. There's a single thread and then a BLAS operation, which I can do in parallel, and then a single thread. Bulk synchronous processing. So those are the two things about this algorithm. It updates a lot of data, and it does bulk synchronous processing. Fork join model of parallel computing. And that leads to poor performance. In the 70s, what do we know? We didn't know any better, I guess. In the 80s, we did a little bit better. We said, look, these architectures now have cache. In this cache, I can store things and get reuse. And if I structure my algorithm correctly, I can organize things around a matrix multiply. And we know matrix multiply does really well on architectures, because you do get reuse. So LAPAC was looking at cache-based algorithms. And it was really structuring things for shared multiple processors, shared memory machines. And what it did, instead of doing one column, it took a bunch of columns. It took a panel. It went off on the side and said, what do I need to do to introduce zeros in this panel? Those are the transformations. And then it applied that whole sequence of transformations to the rest of the matrix. That application was not a rank 1 change, rank K. A rank K change is a matrix multiply. So I get the benefits of matrix multiply, no additional floating point operations, exactly the same number, exactly. Same round-off error properties, no change in the answers, and the benefits are matrix multiply use. So now I have a chance of getting higher performance. So that was the big deal about LAPAC back in the 80s. The algorithms were basically the same though, bulk synchronous processing, loop level parallelism around that panel operation. So the panel says, introduce zeros in the panel, do some swapping to stabilize things, do a triangular solve across a panel, and then do a matrix multiply. And that was the basic operation, the basic iteration of the algorithm. And that worked pretty well. Along came the 90s and message passing. So we had to take all that software and introduce data distributions and message passing into the algorithm itself. But we decided to use the same basic algorithm. So the same basic algorithm, just the data distribution was critical. And we did a 2D block cyclic distribution of the data. So we got a matrix, we're going to divide it up into blocks, and we're going to assign them to the processors in a very regular way. We assume that the machine we're going to run on has a logical 2D grid of processes. So think of P by Q grid of processes. We're going to distribute the data across that in some uniform way. Uniform so that we get the best potential use of the processors. And that went, okay, so that just says we did this, and we got a picture of a very old computer now. We wanted to make the transition from this to this easy. So we introduced some stuff. So we were writing in C, of course, but we had an interface which was Fortran. And the interface said, in the LAPAC days, we have a routine we're going to call, which is of this, for given M and N, the size of the matrix. We have a pointer to the beginning of the matrix. We have an LDA to describe the leading dimension of the array. And then we make a call to a routine. And that would define how it's done. LAPACK, we have this distribution now. The matrix is distributed across the ensemble of processes. The matrix is still the same. It's M by N, so that's a global thing. Each process has a part of the matrix. We pass in the address for that part of the matrix. And then we have this, where we're really intending to point, we actually pass those in explicitly. And then there's a descriptor. The descriptor basically gives the context. It talks about the logical grid of processes. It talks about the block size, how things are decomposed, and it gives the shape and form for how the data is distributed. So it's through that use of it's through the use of that thing, that object-oriented thing, inside of this routine that we can figure out where we are and what needs to be moved, sent and received in order to make the operations work. So that descriptor was very important for that context. So the matrix, is distributed in this block form. The output comes back in the block form across the processors, and that's how we left it. So the user is responsible for distributing the matrix, making the call, and then figuring out where the answer is in this process. And just so to make it clear, this is the global view of my matrix. These are the processes that I have. This is a 2 by 3 grid of processes, and the data is going to be distributed by blocks. So that's a block. That blue thing is a block, and we're going to divide up the matrix in this cookie cutter fashion, and then spread them around. And we spread them around to get good load balancing, of course. So process 1, gets that guy, 1, 2, et cetera, and that goes on throughout the course, so that we have one process has all those blue blocks from the global matrix, and that carries forward for the whole matrix. So that's the user's responsibility. You had to do that. We had routines to help you do that, of course. But that was the user's responsibility before calling the LAPACK routines. And again, LAPACK used the same basic structure as LAPACK, trying to get leverage out of those blocks. Again, it was loop level parallelism, bulk synchronous in its form, using MPI, running across processors, and that worked okay. That worked pretty well. It's probably still looked as something to compete against if you were going to run a code. Today, we're going to do things a little different. So the LAPACK routine, again, I just want to emphasize what it's doing. This is the LAPACK structure. It's bulk synchronous, loop level. We have a sequential thing, then we do something in parallel, sequential, parallel, sequential, parallel. And if you're going to think about it, there's a sequential thing and then a bunch of things to be done in parallel, sequential, parallel. And the operations are listed here that we're actually doing. And if you take a look at a time chart of this across, let's say, 16 processes in a shared memory context, the colored things are doing active work. When it's clear, those guys are idle. So we're looking at time and a process that's going on here. So this is the process that's active, doing something, probably the very first bit of work, and then a bunch of things do something, and then one, and then a bunch of things, one. So I got a lot of white space. White space is idle. Those guys are not productive. So you can see from that we're going to be not running at its peak performance because of the fork join, because of the bulk synchronous processing. So what we want to do is get ahead of ourselves. That is, we're going to do step number 1, but before we finish step number 1, we want to start step number 2. So before we finish, we want to start the second part. So I want to actually, so this is the way it works. So this is the old way it works. Level 1, do level 2, and then level 3. And as soon as we can, we want to start this guy so this guy can begin. So we want to start this process as soon, even before these guys finish. They don't contribute to this operation here. It's just this guy. And you can see by, if you continue that, think of it as unrolling the outermost loop of this program in order to get a behavior which looks something like that. And if you do that, then you unfold basically a directed acyclic graph of the algorithm, a DAG of the algorithm. And this is the old way in which that was executed. If you execute that DAG respecting the dependencies, looking at the critical path in the DAG, you can end up with something which looks like this in terms of the time, execution time. So you get a compression that goes on. We're squeezing out that white space. We're getting rid of some of that loop level parallelism. We're overlapping things as much as possible from one iteration to the next. And that allows us to do better. So layouts are important. I mentioned laying things out in a Fortran-centric way. The algorithms that we're dealing with today lay things out in a tiled fashion. So we're thinking of tiles of a certain size, laying things sequentially that way. So we have this contiguous bit of data that we're going to be drawing in, and that enhances the performance that we see. This is the LAPAC way of looking at an algorithm. It looked at this panel-based approach, structuring things to update things in a certain way, using the BLAS operations to do that. The way we're doing it, the new way we're doing it, is based on tiles. The tiles are smaller, and it leads to a little bit finer granularity of the operations. So I'm not doing a big operation like this. I'm breaking it up into smaller operations like that. And that has an implication. Implications are that this was a rank K updates for a symmetric matrix, and here I'm actually doing small gems, small matrix multiplies. Matrix multiplies are good for performance. Same number of floating point operations. Haven't changed the basic operations, just made things better. The DAG that evolves, this is the DAG for LAPAC, very loop level oriented. This is the DAG based on this tile-based approach, looking at the dependencies between those tiles. We get something which is shorter. So shorter is better. This is a small example. For a bigger example, to be more dramatic in terms of the time to solution, this is the critical path. You want to minimize the critical path. Execute that first, and you'll release the most parallelism that you can in your algorithm. So that's an important thing to focus on as well.
So is this something you're working on now, or is something that is done?
This is a done deal. So this is Plasma. So these are algorithms in Plasma. This is the structure at which we worked on. So all of these ideas are going into Slate, which is the next project that we're working on. Think of it as research going into production level hardened things. You can download Plasma today and use it. It does this. It does this using, let me just carry on a minute and I'll show you how it works at a finer level. This is the LAPAC structure. Again, loop level. The black spots here are idle times that we have. You can see panels that are working. You can see the operations that are encoded in colors. And this is the Plasma version of that. The execution is shrunk because we have this DAG. It managed to get more overlap. It manages to free up this loop level based bulk synchronous processing, and we get a reduction in time. So that's the good thing. So again, these are processes. This is the evolution of time, and you get an overall benefit. In this particular case, 24 cores, shared memory machine. So we're using OpenMP. So this is in Plasma. We use OpenMP. Task-based things are there, so we can actually describe the DAGs. I like to think of it this way. I write a program which generates tasks, and then the runtime system will take those tasks and execute them respecting the dependencies. So basically my program is just generating work, and then the runtime system on the back end, which is used in OpenMP, is doing the actual execution of that work, respecting the data dependencies, the inputs and outputs associated with that. So I describe the inputs and the outputs, and that's what drives this algorithm. So this is a code fragment for doing that using the OpenMP pragmas. where we describe the inputs and outputs, what is input, what's output for this, and based on that, the scheduling mechanism within OpenMP will do the job. When we started Plasma, we wrote our own scheduling system called Quark, and that was before OpenMP had its runtime system that was able to do this. And we're happy to use OpenMP. It's efficient, it's as good or better than our system, and we don't want to be in the runtime business. So we're happy to do that. So I would advocate it. Okay, so Plasma does this stuff that's available today using OpenMP. Magma is a package I haven't talked about. That's a version that runs on GPUs. So if you have an accelerator, Magma would be the package you could look at. dPlasma is the parallel version of Plasma. So again, DAG-based approach. And Slate is the project we're working on today. So this project is part of the ECP project. And ECP will end, or will run out of funding in September of 2019. So this will be finished in 2019, guaranteed. So it's based on C++. It uses all the stuff I've talked about. It'll have hybrid algorithms, distributed base things, and it'll be the state of the art as far as we know. Okay, I want to shift gears a little bit. I have, what, another half hour? Oh, sorry, there's a question. Yes, please.
Yeah, I have a question. Why did you choose C++ for Slate? What was the reason?
It allows us to program a little bit easier. We define our data structures in a much more natural way. We can change code from one precision to another in a very flexible manner. Performance is not an issue. It's an old thing that people harp on that I don't think is true today. Many of the packages that we have are in C++. We're going to hear about Trolinos, I think, at some point in this discussion, and that's a C++ implementation of things. We just felt it was time to upgrade and to get with the times.
So you are saying that the development, in terms of development, it is kind of easier and more composable?
Absolutely. So from a software engineering standpoint, it makes our job a lot easier. And
you see no difference in performance at all?
And we see very little difference in performance, and those differences are not anything to worry about, in our mind anyway. Yeah. So I would say if that's an issue, you should try it, but I would expect things to be good in the end.
So if we want to use it, we have to learn C++?
No, not at all. So not at all. No. So that's one thing that we're conscious of. Many applications are written in Fortran today, and we will have a binding for Fortran. In fact, we're going to have a binding to LAPAC. So if you have an old code which used LAPAC or ScalaPack, you can call a routine that we will have which looks exactly like that, which uses Slate underneath. So things will happen underneath the covers to make that work correctly. Yeah.
In my group, we link with the math kernel library, Intel's math. Yeah. Can you compare?
So MKL is Intel's thing, and maybe Tim will talk about that in detail, but probably not. No, Tim's not going to give you. Tim's not talking at all. I don't know what are you talking about. That's right. Okay. Fair enough. So MKL is what you can get from Intel. Intel has a wonderful version of the BLAS library. That's state of the art. That's good stuff. We use it. I would advocate people using it. Never download the version of the BLAS from netlib and expect performance. The version of BLAS that are in netlib is the definition. It's not the one you should be running for performance. Just to make that clear. But let me just go on. So we work closely with the MKL team. So we have monthly calls with those guys. And unfortunately, it's a one-way street. So we tell them, we're comparing our routines with your routines, and our routines are this much faster, and here's why. And they take that information. The next release, their routines run the same as our routine. And we say, what are you doing inside? Well, we can't tell you. Okay. But you can figure it out. We can figure it out. Sorry, was there a question over here? Yeah.
So the DAG that you talked about in Plasma DAG, is it executing only on the CPUs? Like, can a part of DAG execute on CPUs and GPUs at the same time?
Yes.
Using different tile sizes or something like that?
So if we have a hybrid machine like Summit, which has has GPUs and has things. We have a runtime system, and that runtime system manages the tasks. So parsec in our case is our runtime system. But we can replace that with anything you want. Any runtime system is fine. We need a runtime system. The runtime system has the guts or the information about, it has the DAG, of course, it has the information about dependencies, but it also has information about what operations and what the cost is, how much data is to be moved, and where it makes sense to do that. So it's making decisions about how to do that. So we want a uniform tile size, but it may coalesce tiles if it has to. It may. Right, so it's doing things at a different level there, trying to get performance. So there is that runtime system, which is critical in terms of the performance. So we think about, the way to think of this is, we statically schedule across the nodes. So I could tell you precisely what's going to be done on a node, and then the runtime system dynamically executes its stuff on the node, whatever the node is. So I can't tell you that it's going to run on this process. I could say it's going to run on a node, but I can't tell you which part of that node it's going to run on ahead of time. During the execution, it's dynamic. So that's the way we structure things. So deep learning. So this is the big elephant in the room, right? So this is really the killer app for high performance computing. And we're seeing it in many different areas today. And if you take a look at deep learning, it's about linear algebra, right? It's about matrix multiply. It's about matrix vector operations. And there's this joke. It says, is this your machine learning system? Yep. You pour data into this big pile of linear algebra, then you collect the answer on the other side. What if the answers are wrong? You just stir the pile until you get the right answer. Right? That's sort of the way I think about deep learning. I understand how things could be done, but then there's things there which I don't get yet. How many levels do you have? What are those levels detecting? How do I set up a level? How do I actually do that implementation? How many stages are? So there's so many things there that are cryptic. There's not a blueprint for doing it in general. But matrix multiply is a fundamental thing, and you don't need 64-bit floating point arithmetic. So those two things are critical, and that has not been overlooked by the vendors. So this is a short table of the vendor stuff. Oh, I should have removed this. So Intel no longer is doing this. This is a big red X here. Right, so they no longer have Knight's Mill. AMD has stuff for doing 16-bit floating point arithmetic. So 16-bit floating point arithmetic, there's a standard. ITripleE defines it. And that's the definition. You get 10 bits of fraction, 5 bits of exponent. 5 bits of exponent. That says the biggest number I can have is 65,000. If the number gets above 65,000, I overflow. Okay, now I've got a problem. Right? So from a numerical standpoint, the dynamic range is very limited. But given that's what it is, everybody here and their brothers say, we're going to do this. So NVIDIA has something which, if you do things correctly in 16-bit arithmetic, gets 120 teraflops. 120 teraflops. This is one board. Think about Summit. Summit has 4,000 nodes. Each node has 6 of these Volta chips in it. That's 3 exaflops. 3 exaops is the way they would say it. So we're already at the exaop range if you take a look at 16-bit arithmetic. Google has something. Google has their TPU. Google's thing is a little bit more interesting, since they said, forget about IEEE arithmetic. We're going to do things this way. And the way they do it is they have those same, they have a 7-bit fraction, and they have an exponent, which is 8 bits. That 8-bit fraction, 8-bit exponent is the same as 32-bit arithmetic, the exponent of 32-bit arithmetic. So the dynamic range is a lot bigger. So they have a better, from a numerical standpoint, a better way of doing business. I don't have this, I haven't had a chance to kick the tires here. We do kick the tires there, and that's what I want to talk about. Okay, so here's what we have. We have on our machines double, single, half precision, and quadruple precision if you want. Those are what IEEE defines, and this is the definition according to IEEE arithmetic. And there you can see the ranges of our numbers. 10 to the 5 is the max range of our numbers with 16-bit arithmetic. The Volta, which is on Summit, has 4 performance ranges. This is the way I think of it. 64-bit performance. This is out of one board, one Volta. 64-bit, the peak performance is 7.5 teraflops. Think of matrix multiply, we get pretty close to that, 7.5 teraflops. 32-bit arithmetic doubles it, 15 teraflops. If you do half precision using the FMA instruction, you double it again, 30 teraflops of performance. They have a special instruction. That instruction deals with something called a tensor core. Tensor cores do 4x4 matrix multiplies. So if you do a 4x4 matrix multiply, 16-bit arithmetic, it runs 120 teraflops. So you see the big difference there between those performance ranges. Incredible. But you have to do this matrix multiply. So multiply 2 4x4 matrices together and get a result. And it's a little bit funky, the matrix multiply. Internally, they do 32-bit arithmetic. So you get more than you deserve internally. So you get better accuracy inside the routine. Out, when you finally truncate, you go back down to 16 bits, you go back to the ITripleE format. But inside, you get better than you should because of the representation of numbers internally. And that's sort of another key thing, running at 120 teraflops peak. Okay, 16. So the way we think of it is 16 bits in, multiply, accumulate 32 bits, and then output, which you feed back in to do that kind of operation again. So this is what we see when we run matrix multiply on one board of a Volta. So this is a 64-bit operation. This is a 32-bit matrix multiply. This is a 16-bit half precision, not using tensor core, just using FMA instruction. And this is the tensor core performance. So much higher performance, 16-bit arithmetic using the tensor core structured around matrix multiply, 4x4 matrix multiplies. So if you can do that, you could extract really high performance. So we're reaching about 85 teraflops. 120 was the projected or theoretical number. That's for square matrices which are big. Unfortunately, my matrices for my algorithms are not like that. I've got matrices which have this shape. They're a rank K update kind of matrices. And when I do that, I have more communication, and that drops the performance for all these routines a bit, although most notably for the tensor core. So I lose about half the performance for the tensor core because of doing rank K, smaller size matrices that have this kind of shape rather than this kind of shape. Just to keep that in mind. Okay, so what happens when I do an implementation? So this is an LU factorization of a matrix. And looking at doing LU 64-bit, 32-bit, 16-bit, not tensor core, 16-bit tensor core. So you see the performance difference that you actually achieve doing that operation to completion for various sizes of matrices. So I'm intrigued by this, and I'm intrigued because what I really want to do is extract as much performance as I can, but get the highest accuracy as well. So we have some algorithms in our collection which perhaps can do that. They use mixed precision. They do the bulk of the work in half precision or short precision, and then they refine the solution using higher precision. The bulk of the work, n cubed, is done in the short precision, 16-bit, and then the refinement is done maybe in 64-bit. And the expectation is the answer will be as good as the 64-bit. Now what we want to see is the bulk of the work in 16-bit, and then the iteration part to refine the solution to be less work than we did with the bulk of the work. Otherwise we won't gain anything. So we have some algorithms which do that, and the algorithm I'm going to be talking about is basically a form of Newton's method. So Newton's method says, look, we have a solution. We think about updating that solution to get a new guy, and if we rephrase that just slightly, we have a correction that we're going to make, and that correction is based on this computation here. So the important thing is it's a correction to the solution. So I have a part of a solution, and I'm adding a correction onto it. That's the way you should think of this procedure. So I have a solution which has low accuracy, and I'm adding something which gives us a higher accuracy. Okay, and of course the addition is going to be done in the higher accuracy part. That is when you add those two pieces together, so you can refine the solution. Okay, so mixed precision is what we're going to be looking at, and we want to achieve a faster time to solution. We're going to get some energy savings as well. There's a paper that's here that I've referenced. We were just told that we have a paper that's going to appear in the SC conference, which is the real paper, the paper which has all the real cool stuff in it. Okay, so here's the algorithm. It's called iterative refinement. So iterative refinement for systems of equations. So I want to find AX equals B, and what I want to do is to compute a solution to a higher precision, but I want to exploit this factorization here using low precision. So this computation is going to be done in low precision. That's order n cubed work, factoring the matrix, LU factor. The solution part is going to be done in low precision. That's order n squared work. Compute a solution and approximation. I compute a residual. So the residual says, how good is my solution? So I do B minus AX, where A is the original data. I have to have a copy of the original matrix. That's a penalty of this algorithm. I have to have a copy of the original matrix. And that's done in 64-bit arithmetic, but that's n squared operations, matrix vector multiply. And then I iterate. I iterate while this residual, until this residual is small enough. And what I'm going to do is to compute this solution here. AZ equals R. R is the residual. Z is a correction. That's that correction, x plus, or xi plus 1 minus xi. That's what Z is going to be, really. That's what I'm going to be computing in this case here. And then I go back, I correct the solution, and I do compute a residual, and I iterate on this loop. These guys have to be done in 64-bit arithmetic. This guy here, this factorization, or this solution part, this computation here, classically, it's done with the factors I have from the matrix. The factors I have from this matrix here are used to compute that correction. That's L and U that are used there to correct that, with the right-hand side being the residual. And that's order n squared operations. And that's done in the lower precision. So I get a correction in the lower precision, and when I add that to my approximation, I get an answer which has more accuracy than I should have had if I just think about the lower precision. And I continue iterating that until it converges. That algorithm works well. It works so well it's in LAPAC. And the lower precision is single precision. The 64-bit is, of course, double precision. You need a copy of the original matrix, and there's a caveat. The matrix can't be too ill-conditioned. The conditioning of the problem will destroy this solution so we get no digits of accuracy. If I have one digit of accuracy here, if I have an approximation with one digit, then the algorithm converges. All right, so that's the only caveat. And I have to have a copy of the original matrix in double precision. Recent results by Nick Hyam and Lynn Carson says, don't compute this using L and U. Don't compute this using L and U. Use an iterative method. Use GMRes. You got a dense matrix, but you got a pretty good preconditioner, the L and U factors. So it should converge very rapidly, and it does. So we use this iterative method here to compute that Z, and it doesn't infect the solution with the conditioning. So we don't have that condition problem. That's released. And that algorithm runs pretty well. So here's some convergence histories. So think of 64-bit results. We get the right answer. There's no story about convergence. We got the right answer. This is using 32-bit arithmetic. It takes about 3 iterations. If we do 16-bit arithmetic using the tensor cores, it takes another iteration, 16-bit arithmetic, 16 bits, internal for this for the factorization, and then do the iterations using 64-bit. If you use the 16-bit arithmetic, not tensor core, remember tensor core has this funky property of doing some additional precision that you shouldn't deserve. This doesn't do that. It just uses 16-bit arithmetic. So it takes a bit longer to converge, but it does. So we get the right answer. This is what it looks like in terms of performance. So this is the performance for the 64-bit operations, double precision, half precision. This is the 16-bit arithmetic performance, not tensor core, and that's the tensor core getting it. Same accuracy. Each of these get the same accuracy. This guy got the same accuracy as this. It took 4 times less time to solution. Time to solution now we're talking about in order to get to that point. So there's something there we should be looking at in terms of exploiting that. It takes a few, and this gives the iteration count, if you will. This is the condition of the problem. So the conditioning is 10 to the 5. If the matrix is larger than 10 to the 5 condition number, then we're going to be in trouble. So that's going to be stressing us. Okay, I see I'm out of time here. I'm not going to go through these slides, but it's the same kind of story. I'm just giving you highlights when it may not converge or converge slowly. I just want to pause on this. This is the energy profile of a Volta running this algorithm. This is 64-bit arithmetic, doing the solver, just doing the solver, getting the right answer. This is doing the 32-bit iterative refinement. This is the iterative refinement step. That's how much time it takes. And this is the energy profile, or the power profile. The power is 460 watts, and the energy consumed is given here as 1,000 joules. 2,000 joules was consumed for the 64-bit. The 32-bit iterative refinement was about half of that. This is the 16-bit arithmetic, not tensor core. We're getting to on the order of 600 joules. Flops per watt, that's another interesting number. How many flops can you do per watt? Here we're at 48 flops per watt. When we use the tensor core, things even get better, and we see that we're at 74 gigaflops per watt. That's an interesting number. That's what we need to be for exascale, right around that point for the exascale computer in double precision. So there's something there. I'm going to have to stop here because I'm chewing into Tim's time.
Yeah, I'm getting pissed.
I know you do. You get really mad too. So here's the important things, or the things that I'm interested in looking at. There's a lot of stuff there, but this is what makes it exciting for me. I'm going to stop there and let Tim take over. I'd be happy to answer one quick question if you want. Otherwise, we're going to. I'll be around for the break, and we can talk at the break. Wait, yes, sir.
Yes. Regarding the first part of your talk,
yes.
why LAPACK is used as a benchmark suite for supercomputer instead of LAPACK or Scalec LAPACK?
Right. So okay, that's a good question. So LAPACK is a name. LAPACK was the original benchmark, but today we use something called HPL. HPL is a version of the LAPACK routine, only the race car version of the LAPACK routine. So it's implemented very well using block techniques, using overlapping of trying to get rid of sort of like a DAG-based approach, in fact. But it's not the LAPACK routine. The LAPACK is just a name. It's carried along. It's part of my sins in life. Yeah.